resistance. We've talked about current, and that's how fast electrons pass through a circuit. Voltage is how much energy they have, and resistance is a measure of, well, it is anything that causes the current, the electrons, to slow down in the circuit. Okay, and it is a measure of, and you can measure it. Okay, so anything in a circuit will cause electrons to slow down, right? The wires themselves, but most of it's where the energy is used. Bulbs, motors, laptops, and it involves a slowing down of the and also a loss of energy, because if you feel heat, that means there's electrical resistance causing that. In that way, electrical resistance is a lot like friction or air resistance or something like that. It's the same idea. So sometimes we actually take something called a resistor, and this could be put onto any circuit board, and it's added there on purpose, right? And the purpose is to actually, for some reason, you want to slow down the current, and that could be because maybe the next part of the circuit can't take as much current as what was before it, something like that. So they actually add a resistor to slow down the current, and it takes the electrical energy, and the things actually get hot. So if you build any of the circuits choose that as a lab, and you touch the resistors, you'll notice that they get warm. So to calculate electrical resistance, there's a few different ways I'm going to show you today, but the basic calculation based on circuit properties is it's volts divided by amps. V is volts, I is amps, so volts divided by amps. The symbol for electrical resistance is R, and the unit is ohms, after George Ohm, who came up with the relationship. Okay, so he came up with this equation right here, so they named the unit for resistance after him. Just an example of using that equation. So if in my laptop I got 3.5 amps, and the potential difference, the V, is 19 volts. So to calculate resistance, it's as simple as, if you just follow through, givens, required, and R equals V over I. So you just calculate, give it the unit of ohms. Really good little, well, I think the lab on this is worth doing, but also the textbook questions, just so that you practice this. And sometimes, what if you're solving for V? What if you're solving for I? And I can help you get all the rearranged forms if you need it. When you're looking at a wire itself, there's certain things in the wire that can cause more or less electrical resistance. And for example, the length of the wire. So what this is supposed to say is that, the higher the length means the more resistance, which I hope makes sense. It's just the idea that you've got more, you've got more friction, so to speak, between the surfaces of the wire. So there's going to be more resistance. So the term we use is directly proportional. So if the length goes up, the resistance goes up. We call that directly proportional. And it gives us, this is the formula. But I think when you see the questions, you might not need to use the formula. Okay, so it's just saying, if I had some length of wire and it had this much resistance, 1 being initial, what if I added another, had a new length that was bigger? Well, then that would be the new resistance. And you could rearrange this to find one or the other. But like I say, when you see the question, you'll realize you don't really need to use the formula as long as the numbers are reasonable. The other thing that affects in the wires electrical resistance is the cross-sectional area. So basically the thickness of the wire. Okay, so if you have a thicker wire, you have less resistance, and that's why this is inversely proportional, because when cross-sectional area goes up, resistance goes down. Okay, and again, the idea there is, a better analogy would be water flowing through a pipe. You get a really skinny pipe, there'd be a lot of resistance to the water flow, right? But if you opened up and had a thicker pipe, more room for the water to flow through, you'd have less resistance, and it would flow through easier. It's the exact same thing. A bigger wire, there's more space for all electrons to get through. So just an example. Imagine you had 10 meters of wire and you had 20 ohms of resistance. So that particular type of wire resulted in 20 ohms of resistance. Well, what if I add another? If I doubled I'm doubling the length of my wire. What's the new resistance going to be? And there's the givens. You could use the equation, but really, this is to me the easier way to solve it. Just say, okay, because it's directly proportional, Doubling the length will double the resistance. So my new resistance is 40. Okay, and that's how you solve a problem like that. And you can expect to see something like that on your test. Cross-sectional area. Imagine I had a cross-sectional area of 1 millimeter squared. So they're obviously wires are tiny, right? And my resistance was 100 ohms. An engineer reduces the resistance by changing the wires to thicker wires, three times thicker. What's the new resistance? Okay, and so you remember here, more thickness, the thicker the wire, is less resistance. So you might want to make a prediction on what the answer is going to be, and then here's the answer. I'll show it to you. It goes in the opposite direction. So increasing, if area is tripled, resistance will be reduced by a factor of 3, so it'll be a third, so 33 ohms. Okay, so the area and resistance go in the opposite direction of each other, where length and resistance go in the same direction. Okay, another little bit on resistors is the color coding system. So I put this picture of the textbook here. This is the textbook that I'm talking about when I say, in this textbook on page 329, you'll find a table that'll help you figure out, if given a resistor with the color coding scheme on it, how to go back to, what is the resistance on this thing. Because some engineer designed this thing, right? Some engineer designed this resistor so that it would slow down the current by a very specific amount. So we can figure out how much resistance they put in this thing, how much energy is going to turn to heat, by following orange, orange, brown, gold. Because if you look at that table, which is right here, this is the table, what it looks like, here's the orange, orange, brown, gold it was, right? So here's how you do it. You list down the numbers for the first two bands, and it's orange and orange. So you write down 33. You don't write 3 times 3, anything like that. You actually just write 3 and another 3 right beside it. So it's 33. The third band was brown, and the third band is what we call the multiplier. So if you go down to brown and come across to multiplier, it means you're going to multiply it by 10, right there. So you take your 33 multiplied by 10, and that gives you your answer, which is 330. That's the resistance. And then the final band, the gold, ours in the lab are all silver, but this one's saying gold, and it's down here. The fourth ring refers to the tolerance. And what that means is, and this isn't that important for you, it's just the idea of a gold resistor would be a higher quality resistor than silver. Silver's tolerance is 20%, and if it doesn't have a band, it's silver's 10%, and no color is 20%. And what that means is, it's how precisely made it was. So, when we say 330 ohms for this particular resistor, well, really it could be, there's a range, right? It's not made perfectly. And that's what that last band tells you. So a gold is a higher quality resistor with a lower tolerance, meaning it's more precisely built. And then silver is less precisely built. This is what we have in the lab. And then it has no color, no band at all. Then they're not very precise, 20% difference. Okay? Looking at another example then, orange, black, red, gold. So remember, you take the first two digits, or first two colors, and you come up with your first two digits, which will be 3 for orange, and black is 0, so 30. The red refers to this one right here, ring 3, so it's times 100. And again, gold, and the gold is plus or minus 5%. So this is the answer. Like, I'm not going to bug you too much about this. This is figuring out 5% of 3,000, subtracting and adding it. This number here is the one that you should be concerned with, okay? I think in your lab, it's actually pretty good. In the lab, ask you to, you're going to calculate the resistance by building a circuit measuring volts and amps. And then you say, okay, so my calculated resistance was whatever. Say it was 3,100 if it was this one, okay? And then the question is, would it be within the tolerance of that resistor? And if it was 3,100 and it was this resistor, it would be fine, okay? And that's the idea in the lab, and it's pretty good. It works pretty good. All the electricity ones work well. I think that's the last example. Yep, that's the last one. So that's it for electrical resistance, and